assume, going into the test?
That the normal will happen.
That the normal, and what is, good, thank you. And what is the normal if you drink caffeine? The status quo, thank you. And what is the status quo? You drink caffeine? Or, at worst, it doesn't do anything, right? So, I've drawn a bell curve because I'm allowed to, because we've drawn a sample. And the central limit theorem guarantees us a bell curve. Correct?
Yes.
And the central limit theorem says your sampling distribution is going to have as its average whatever the average heart rate is for unchanged people. So you don't drink a bunch of caffeine all you want. Guess what? Your heart rate's going to be exactly the same as it was before. Okay, maybe not. Maybe it'll get higher. Maybe it'll go up. Maybe it'll really go up. Maybe it'll go up so high that you pass out. But that's the elevated heart rates, yes? Okay, so here's average. Exactly average. But we know statistics, you can't land exactly on average. Maybe you land a little bit below average, which isn't statistically different from average. But what happens as we start going down here?
Closer and closer to showing the unusual.
The heart rates are dropping so much, they're dropping so much that they're considered to be unusually low. Now there is an unusually high over there as well, of course. But exactly, but we weren't testing that because that wouldn't be unexpected. What would be unexpected is caffeine lowering heart rate so much that it pops into this range over here. So, let me ask you a question. Harrison, you mentioned 95%. Where is the 95%? Uh-huh. All the blue or the green? Blue. Yeah, all blue. I'm going to go with blue. I'm going to go with blue. I suck with colors. All the blue region up there is 95%. Now that looks like a confidence interval, doesn't it? How does it look different than a normal confidence interval that we're playing with?
Because all 5%'s on the left.
Say it louder, Harrison.
The whole entire 5%'s on the left for unusually low heart rate.
Sherry, you drew a picture in the air about 2 minutes ago. When he mentioned 95%, you went, oh yeah, boom, boom. So she went 2.5, 2.5. But that would be if you were looking for excessively low or excessively high. We're not looking for that. We're just looking for excessively low. So we want all that 5% to be down there in that tail, which means we then have to shove this guy up a little bit to make room for it, right? A 2.5, 2.5 would be closer down to here. That means that the 2.5 is over here, and this little remainder here is also 2.5. We've got to give that back to that tail, and then pop out like this, which makes it a one-sided confidence interval. Why this is not taught in the curricula of 244 is beyond me. I would love to teach you guys one-sided confidence intervals as well as two-sided, because this will make a little more sense. But it sounds like you guys are making the connection visually at what's going on. The 95% of usual, which should happen, is in this bluish-greenish 95% area. If you land down here, something interesting happened. Something interesting happened. Now, let me ask you a question, a leading question. Is it possible that we exist on this curve, right? This curve, and we just so happen to get data that fell down here in this tail? Is it possible that nothing unusual happened and we just got deviant random data?
Yeah, because of the subjects.
Of course, we could, even if it wasn't the subject, just randomly we could have gotten it. For example, if you're testing that a coin flips heads and tails at 50%.
You get head 6 times.
If you get head 6 times in a row, that can happen, can it? That can happen. But it only happens 1 in 64 trials, if you will. It's a 1/64th chance of that happening on the first 6 flips. That would put it into this tail, of course. And it would mean that the coin is fair. So you can land down here and say, oh my God, it looks like heart rate actually is lower than this average right here. But it might not be. It might just be that it's living in that tail. Remember Max dropping little balls at OMSI into that thing and from 243? Every once in a while, one of the balls ends up in the far right-hand side. But the key term is every once in a while. This is why study replication is so important. Because if this study gets replicated again, and they end up in that tail again, all of a sudden you go, you know what? It doesn't look like an outlier anymore. Because the chance of getting 2 outliers in successive independent trials would be 5% squared, which essentially bottoms to 0.
Your margin of error is smaller and smaller.
Boom! Yes, and your margin of error, which means these bad boys tighten up. I got a nice little Excel sheet to do that with us later. Yes, thank you. Did you guys buy that? Does that make sense? No. Tell me what you don't buy. Renee, go. No? You sure? I think we're gonna take 5. This is 9 o'clock. Take a little 5 here. But I want to come back and keep looking at this. I want to see where the other 2 levels of exercise live. This was only sub-maximal exercise intensities. It was just sub-max exercise intensities, not max and not at rest. Try to hypothesize where those data are going to fall. This is where the data fell for the sub-max exercise. Based on the p-values that we got for the other ones, see if you can think about where they're going to fall in the curve. We'll come back.